Hello everybody, and welcome to our next webinar dedicated to transformer simulations with QuickField. My name is Vladimir Podnos. I am Director of Marketing and Support, and I will start from discussing the QuickField capabilities in relation to transformer simulations. And then my colleague Alexander Lubimtsov will continue with the presentation of QuickField transformer simulations for different test problems. So on this slide you see a set of QuickField analysis models available today. They include infrared analysis, heat transfer, and stress analysis options. Electrical transformer transfers the electromagnetic energy between circuits through electromagnetic induction. This is a process of physical effect. Then currents are induced in conductors which are subjected to varying magnetic fields. So obviously magnetic simulations are in the mainstream, and they are most commonly used for simulating of the main physical process in the transformer. However, other QuickField models are often required for solving practical engineering tasks. For example, electrical insulation analysis may need electrostatic, conduction, or transient electric analysis. Thermal considerations may require static or transient heat transfer simulations, and stress analysis may be helpful to estimate the transformer construction stability. All processes in the transformer are connected, and multi-physics approach is often quite necessary for transformer analysis. Heat is generated by electromagnetic processes, current and core losses. Deformations are caused by overheating or magnetic forces. QuickField allows coupling. This is connecting of several types of analysis. For example, results of electromagnetic simulation may be used as input parameters for heat transfer simulations. Transformers often have complicated design, which requires non-uniform meshes with high number of finite elements for needed accuracy of simulations. Large meshes make the computational task very intense, and fast and efficient solvers of QuickField give huge benefits. Our solvers are based on the special procedure we call DDM, main decomposition method. And this procedure provides extreme speeds. As you see on this slide, QuickField solvers feature quasi-linear dependency between number of mesh nodes and solution time. In conventional finite element packages, this dependence is often of second order. Practically, it means that in majority of practical cases, QuickField gives results within minutes, not in hours or days, which were traditional cost of finite element simulations before. In addition to graphical user interface, QuickField features also application programming interface, allowing access to internal functions and data structures from other Windows applications. This open object interface may be used for interacting between applications developed in many modern programming environments, including Microsoft Visual Studio. You may use programming languages like C++ or C#. You may use Microsoft Office Visual Basic for applications. It means you may use macros developed within Word or Excel. You may use MATLAB, you may use Python, Lua, etc., etc., etc. In some cases, QuickField components communicate with QuickField core via this interface. This is the way our parametric analysis utility label mover works. Open object interface to QuickField core is called ActiveField, and it includes objects and methods which are explained in detail on our website. We provide plenty of programming examples and free utilities you may use with any version of QuickField, including free student edition. And QuickField difference is most important. All these diverse and sophisticated features are wrapped into very straightforward, easy to use, intuitive user interface. No special training required. Even the high school students may start using it for their class assignments in fully automated mode. Or if the task becomes more complicated, they gradually use more advanced settings and methods. So with growing complexity of tasks and methods, users may start exploring QuickField for more advanced methods of analysis. But to start using QuickField, there is no special knowledge or special training required. The range of QuickField applications is extremely large, both in the types of analysis and in the level of problem complexity. Now my colleague Alex will demonstrate how to use QuickField for transformer simulations in his live presentations.
Hello. Today, 6 simulation examples will be reviewed. First is a single-phase transformer. The no-load mode and the short-circuit mode will be calculated, and the parameters in no-load mode and the parameters in short-circuit mode. Then the single-phase pulse transformer will be reviewed. The third example is the three-phase transformer with non-symmetrical load. Then we will calculate the heating of the transformer and the losses in the transformer. The fifth example is the mechanical stress in transformer windings. And the last example is the transformer tank three-phase bushing insulator. Here is the single-phase transformer. The dimensions of the transformer are 6 by 4 by 4 centimeters. So it's a small transformer. The voltage applied is 36 volts and the frequency is 50 Hz. The primary winding has 440 turns and the secondary winding has 168 turns. Our task is to calculate the no-load current, the secondary voltage, the magnetic flux density in the core, and the short-circuit current. So let's start QuickField. I will create the problem from scratch. So I create the new problem. Type in the problem name. Next, I should specify the problem type. The problem type should be the AC magnetics to calculate the magnetic field in the transformer. And for the AC magnetics, I should specify the frequency of the currents. Also, I should specify the depth of the model. $40 millimeters. And we have windings. The most convenient way to specify the windings connection is to use the external circuit. So I type in the circuit name, the circuit file name here. This is the problem tree, and this is the geometry model window. Here I should draw the geometry of my transformer. And the fast way is to import the geometry model from the .dxf file. Now the model is imported and we should assign the labels to geometric objects. We use labels to identify objects and to assign the material properties and boundary conditions. This is the core. And the label appears in the problem tree. Now this is the primary winding. Direct current and the primary winding reverse current. And this is the secondary winding. Primary current. And the secondary winding reverse current. And we have the boundary. The flux, the magnetic flux of the transformer flows inside the magnetic core, doesn't leave the core, so on the core surface I will specify the boundary condition. Now the geometry model is ready and we should specify the physical properties for each object. For the core, I will specify the magnetic permeability of the core. I specify the constant value here, but it could be a nonlinear material. For the primary winding, I specify the permeability of the copper and the conductivity of the copper. The conductors are connected in series, and the voltage source will be specified in the attached electric circuit. The same for the back current, the magnetic permeability, the electrical conductivity, and the conductor's connection scheme. And the same for the secondary windings, because they are made of the same copper. Now we should open the circuit file and specify the sources and the connection of the winding there. This is the circuit editor. Here I should put all the conductors. I put here the primary winding, the secondary winding, and I should connect the electric source here. .56 volts. That's enough for no load case, but I recommend to attach some large resistance to the secondary winding so that we can measure the voltage drop on this resistance and I set the value of the resistance 100 kilo ohms. That's all for the circuit, and we have the boundary of the transformer. I specify zero magnetic potential here. That means that the flux doesn't flow outside our core. The next important step is to build the finite element mesh. To do so, you should just press one button. The mesh will be created automatically. Yes, we forgot one block, the insulation. And for the insulation, I specify magnetic permeability of insulation and zero electrical conductivity. Now we can simulate the no-load case. This is the flux, the feed lines in our transformer, and the color map of the current density. It is possible to choose the display values. So I will switch on the vectors of the flux density and the color map of the flux density. And you can switch on the animation. Here you can see how our transformer operates in no-load mode. You can see the vectors of the flux density and the color map of the flux density distribution in the core. With QuickField you can measure the field barriers. For example, I can measure the flux density in the core in every point. In our problem, we have the electric circuit, so let's take a look at the simulation result in electric circuit. This is our circuit, and the current in the primary winding is 0.033 amperes. And the output voltage is 6 volts. We can calculate the transformation coefficient. Here I start the Excel file. Now the output is this is the peak value. We should divide peak value by the peak value. So we have 36 volts as input, and the output is 9.33. So the transformation coefficient of our transformer is about 4. Now I will adjust the field picture and switch on the flux lines. Here you can see the flux lines. And here you can see that not all the flux lines are connected to the secondary winding. There is the leakage flux, and you can see it on your picture, and you can measure it with QuickField. So how to measure the leakage flux? First, I will measure the flux that is connected with both the secondary and the primary windings. I will build the contour here and measure the flux that cross this contour. It is 1.68. Now let's measure the total flux connected with the primary winding. To measure the flux, I select the winding. And here is the flux connected with the left side, and the same on the right side. And the total flux connected with the primary winding would be twice this value. Wind 1.79. And this is the total flux. The flux that passes here is 1.68. So there is the difference. There is a flux leakage. Now let's simulate another case, the short circuit case. I will change my circuit and specify some low resistance in the secondary winding. Now I run the simulation again, and here is the flux distribution in my transformer. Now you can see the leakage flux without zooming. The leakage flux now is much greater than it was in case of no load mode. Let's switch to the electric circuit. Here you can calculate the electric current in the primary winding. Of course, in real transformer you should adjust the input voltage so the current will not exceed the rated value. But anyway, you can use these values to calculate the impedance of the transformer. And again, I will use the Excel file. Here I typed some formulas for complex numbers calculation. I will type in the voltage, and I will type in the current. So this is the impedance of my transformer there. The reactance and the resistance. And this is the average power, the active power and the reactive power. And we can calculate the inductance of the transformer. It's very small value because we have the short circuit case. What else you can do with the transformer with QuickField? QuickField allows you to modify the geometry model and perform tests very fast. Let's take a look at the flux density distribution in the transformer. You can see that these corners are not saturated, they are very low flux value, so we can cut these corners and reduce the weight of the transformer. Now I cut the corners and specify the boundary condition, solve the problem again, and this is the flux density distribution. You can see indeed there is no need for these corners in the transformer. The next case is the pulse transformer. The pulse transformer consists of the primary and secondary windings, and there are 13 turns in the primary winding and the 200 turns in the secondary winding. The coils are surrounded by the ferrite core, and the coils carries the pulsed current. The current and the form of the current is the SAW, its periodic function. The current were measured on the real transformer, and our task is to calculate the external magnetic field of this pulse transformer. There is the air gap in the core, and some of the flux is radiated through this gap. So I start QuickField. And this is my problem. The problem type is transient magnetics, because for the pulsed current I should calculate the transient process. Also, I have the electric circuit to specify the windings connections. And for the transient magnetics problem, I should specify the integration time step and the final integration time. This is the asymmetric model. That means that we have the rotational symmetry in the model. And in my model, I will have to draw only the upper half So let's take a look at the unity model. Here I have the air. In this model, I will calculate the field generated by the transformer and radiated through the air gap. So I need the air. I have the ferrite core. And for the ferrite core, specify the magnetic permeability of the ferrite. And I have the primary and secondary windings. And for each winding, I specify the magnetic permeability of copper and the conductivity of copper. The conductors are connected in series, and the sources are specified in the electric circuit. This is the electric circuit. I have the primary winding and the source current in the primary winding and the secondary winding and the source current in the secondary winding. You can open QuickField and check the help of the QuickField to find out what the source function is. This is the source function. So I have the pulsed current in the primary and the secondary winding. And now let's take a look at the results. For the transient problems, you get the results for each moment of time. I switched off the animation so you can see how the magnetic field changes in time. And we have the electric circuit. We can open the circuit results. Here are the currents in the primary and in the secondary windings. And this is the voltage in the primary and in the secondary windings. Our task is to calculate the external magnetic field radiated through the air gap. So I will switch on the color map of the flux density. Let's adjust the scale to get better view. Now you can see the region where the flux density value is greater than 1 millitesla. Also for the transient magnetic problem, for every transient problem, you can take a look at how the values change in time. I will switch on the time plot, and this is how the flux density changes in time in this point. Now let's move to the next example. This is the three-phase power transformer. You can see the dimensions are 35 by 20 by 50 by 5 centimeters. And the phase voltage is 220 volts. The frequency is 50 Hertz. And this is the windings connection scheme. The primary winding is connected in Y, and the secondary winding is connected in delta. And the load connected to the secondary winding is non-symmetrical. We have the active resistance in the phase A, the active resistance in the phase B of a different value, and the inductance in the phase C. The primary winding of the transformer has 2,560 turns, and the secondary winding has 150 turns. Again, our task is to calculate the currents in each winding. So I start QuickField and open this problem. Let's take a look at the problem properties. The problem type is AC magnetics. I will simulate the sinusoidal currents. The frequency is 50 Hertz. I specify the depth of the transformer 5 centimeters, and I specify that there will be the circuit file where the connection of the windings is specified. Let's take a look at the geometry model. Here I have the following objects. I have the air, and for the air the magnetic permeability of 1 is specified. I have the core, and for the core the magnetic permeability of 1000 is specified. I have the insulation, and I have the windings. In this model, 1 denotes that this is the primary winding, and the second denotes that this is the secondary winding. Minus in the name, this is my notation, minus in the name denotes that the winding is located to the left from the leg of the transformer, and the plus indicates that the winding is located to the right from the leg. So I have phase A primary winding, phase A secondary winding, phase B primary winding, phase B secondary winding, phase C primary winding, and phase C secondary winding. And for each winding I specify the magnetic permeability of copper, the electrical conductivity of copper, and that the conductors are connected in series. The voltage source and the load are specified in the external electric circuit. So this is the external electric circuit. I have the three-phase voltage sources connected in Y, the primary winding connected in Y, and the secondary winding connected in delta. And this is the load connected in delta. Let's take a look at the simulation result. This is the magnetic field of the three-phase transformer and the currents in the transformer, the current density. Let's switch on the animation. You can see how the current in the winding changed from blue to red and then again to blue. It changed direction, and the flux changed in flows in one side or in another. You can adjust the field picture. I will switch on the vectors. And we can take a look at the external field produced by the three-phase transformer. This is the non-symmetrical load mode, so the field distribution is not symmetrical. Now that's enough for the field distribution. Let's take a look at the circuit. This is the electric circuit results, and for each element I can calculate the voltage drop and the current. And you may see that the current in the phases are different because we have the non-symmetrical load connected to the secondary winding. And again, I will use the Excel to calculate the impedance of each phase and the power produced by the transformer. These are the values that I get from QuickField. Real part of the voltage in the imaginary part of the voltage, and I get the current values. So this is for the voltage source in the phase A, and I copied all the data from for the voltage source in phase B and for the voltage source in phase C. So these are the powers that are taken from our voltage sources. And on the right side, I have the secondary windings elements, and again for each element I copied the voltage value and the current value and calculated the active and reactive powers. Now let's take a look at the total power consumed from the voltage sources and the total power produced in the load connected to the secondary winding. You can see that they are different. And you may ask why there is the difference between the total power in the primary and total power in the secondary. Well, the difference in the reactive power caused by the fact that the transformer consumes some reactive power to produce magnetic flux in the core. So we have on the primary side the reactive power greater than on the secondary side. And we can calculate the energy conversion coefficient of our transformer. It is 39%. But what about the active power? This is the active power produced by our voltage source, and this is the active power consumed. Why there is a difference? That's because there are losses in our transformer. Here I can see that the difference is about 70 watts. And now I will show you where you can find these 70 watts. I will surround my transformer with a contour. And we'll calculate the joule heat. These are the losses, the active losses in the transformer. So our next task is to calculate the temperature in our transformer. This is the same transformer. I know the thermal conductivity of the copper, of the steel, of the insulation. The transformer is cooled by the air, and I know the convection coefficient. It's 12, and the radiation coefficient 0.9. The ambient temperature is 20 degrees Celsius, and I would like to calculate the temperature. There are two kinds of losses in the transformer: the electric losses in the winding and the magnetic losses in the core. Again, I have the Excel file to calculate the losses. This is the winding name, the primary windings, the secondary windings. I know the conductivity of copper. I know the cross-section of the conductors. You see that the primary winding has the cross-section 6.25, and the secondary winding has the cross-section of 60 millimeters square. So these are the cross-sections of the conductors, and these are the currents. From the circuit results, I can get the currents in every element. So these are the currents for each phase. In the primary winding, and the currents in the secondary winding. For the phase A, for the phase B, and for the phase C. Now I know the currents, I know the conductor's cross-section, I can calculate the current density, and using this formula I can calculate the electric losses density. These are the values. Now let's take a look how to calculate the losses in the core. This is the equation to calculate the losses in the core. Cm is the properties of the material. This is the losses in watts per kilogram. F is the frequency, B is the flux density, and ρ is the mass density of the steel. Now I know the F, it's 50 Hertz. I know the Cm from the material properties. I know the mass density from the material properties. I need to calculate the flux density, the average flux density in the core. To calculate the average flux density, in the core, I should select the core elements and choose the mean square flux density integral. Here the value I need to calculate the losses in the core. So I put this value in the Excel. And now I have the electrical losses in the winding and the magnetic losses in the core. Now I can proceed with the heat transfer problem. I will create the new problem as a copy of the existing one. I call it heat1. The problem type is steady-state heat transfer. I do not the electric circuit for the steady-state heat transfer. So this is the same problem, and here I should specify the thermal properties of materials. I do not the air block. I will calculate the temperature in transformer. The transformer is cooled by the air. So I should label its external boundary and specify the convection and radiation boundary condition. So this is the cooling surface. For each block, I should specify the losses and the thermal properties. For the core, I specify the thermal conductivity of the steel, and the losses I calculated in magnetic problem. For the primary winding, I will specify the thermal conductivity of the copper and the losses. I have the same losses in the direct and in the back side of the coil. And the same I repeat for this secondary winding. Now for the phase B, primary winding. The losses are this value. For the phase B, secondary winding, the losses are this value. For the phase C, primary winding, the losses are this value. For the phase C, secondary winding, the losses are this value. And for the insulation, I specify the thermal conductivity of the insulation. Now we have the losses in the transformer, and we should specify the convection boundary condition on the transformer surface. The convection coefficient is 12, and the temperature outside is 20 degrees Celsius. I will specify the radiation coefficient and the temperature. And before I start the solving the problem, one point I would like you to notice. The transformer is cooled not only by the side surface, but also from the front surface and from the back surface. So to take into account the flux, the thermal flux that seen from the front and back surface of the transformer, I should increase the convection coefficient. "12 from the side surface, 12 from the front surface, and 12 from the back surface. Now let's solve the problem and take a look at the simulation result. Here you can see the temperature distribution in the transformer. And let's calculate from Kelvin to Celsius. The maximum temperature inside the transformer is 94 degrees Celsius. The next important task in power transformer is to calculate the mechanical stresses. So we have the same transformer that is fixed on the bottom and on the top sides. Magnetic forces acting on the windings and on the core. We know the mechanical properties of each material, and our task is to calculate the winding deformation and the mechanical stresses in the core. To solve the problem, I will utilize the coupling capabilities of QuickField. There are two problems. The first one is magnetic problem, where I calculate the magnetic forces acting on each element. And the second problem is the mechanical problem that utilizes these forces to calculate the stresses. So naturally these two problems are linked together. The magnetic forces from the magnetic problem automatically transferred through the link to the mechanical problem. In mechanical problem, I will not calculate the stress in the air. For the winding, for each winding, I specify the mechanical properties of the winding. Also, I specify the mechanical properties of the core and of the insulation. And in problem properties, I added the link to magnetic problem, and I will import the magnetic forces from the magnetic problem to my mechanical problem. So in my mechanical problem, I do not specify any forces. The forces are automatically imported from the magnetic problem. Now let's take a look at the result of the simulation. You can see the deformed shape of the transformer. In fact, it's scaled, so the real deformation will be much smaller. Now let's take a look at the strain distribution. Naturally, the strain appears in the insulation, as the insulation is much softer than the copper or the core. And let's take a look at the stress distribution. The binding shifts and tries to move the core, so the mechanical stresses appears in the core. That is the mechanical problem that utilizes the link between two problems. And the next example is the transformer tank three-phase bushing insulator. This is the transformer tank top plate. The transformer tank is filled with oil. The air is outside the transformer tank, and there is the insulator and the three-phase conductors passing through the steel plate. And our task is to calculate the electrical field stress. To calculate the electrical field stress, I choose the moment of time when the voltage potential of the phase A is the maximum. So the stress will be, electrical stress will be the maximum. Now, this is the QuickField with electrostatic problem. You can see that the model class is 3D extrusion. And the problem type is electrostatics. I will calculate the electric field distribution. What the extrusion means. This is the two-dimensional geometry model, and each object of the model is extruded in a third dimension. Each plane object has several levels, so the three-dimensional geometric model is constructed. And here I have the following objects. I have the air, I have the cover, I have the oil, and these are the insulators, and these are the conductors. And for each object I specify the electrical properties. For the air, I specify the electric permittivity of 1. For the insulators, I specify the electric permittivity of 6. For the oil, I specify the electric permittivity of 2.2. And for each conductor, I specify the electric potential. So this is the real three-dimensional geometry model. Now let's take a look at the results. Here you can see the field distribution. I will hide the air block. So you can see this is the high voltage on the phase A. And now I would like to look inside. I will use the cut plane to look inside my model. This is the voltage distribution inside, and I'm interested in the electric field strength distribution. The electric stress value here is about 600,000 volts per meter. It's smaller than the critical electric stress value for the insulator. And in the oil, the maximum electrical stress is about 300,000 volts per meter. These are all the examples for today. There are much more you can do with QuickField analyzing transformer, but we have no time.
Thank you, Alex. It was very interesting, and I hope our audience enjoyed it as much as I did. And we will publish a recorded version of this presentation on our website in a few days. And we are having much more plans for future webinars. Please check our website pages and subscribe to our newsletter to be informed about our future webinars.